This is the B-52 Stratofortress. The last one rolled off the assembly line in 1962, and it's scheduled to keep flying until 2050. 3 different bombers were built to replace it, and all 3 are leaving service first. But the reason this aircraft refuses to retire has nothing to do with its weapons, its engines, or anything else its designers imagined. It has to do with a single component, one that was classified for decades. Every mission that proves it still works begins here. Inside the munitions facility, airmen prepare weapons that will ride in a bomb bay designed decades before GPS existed. The building stays climate-controlled for the guidance systems, not the people. The electronics inside these bombs drift if temperature swings even a few degrees. Technicians attach the guidance section to the front of the bomb. This is where the weapon gets its brain, a GPS antenna, an initial measurement unit sensitive enough to detect movements smaller than a human hair, and the umbilical connector that lets the aircraft upload target coordinates mid-flight. Without that connection working perfectly, you've got a very expensive paperweight. They bolt everything in place with calibrated torque wrenches. Too loose and vibration shakes it apart mid-flight. Too tight and you crack the housing and destroy a $25,000 guidance kit. Then comes the tail kit, the fins and electric motors that steer the bomb during its fall. Each fin adjusts in increments of 1/10 of a degree, and before any weapon leaves this building, technicians cycle every actuator to make sure nothing sticks or hesitates. A stuck fin means the bomb spirals off course and misses by hundreds of feet. Once built, they weigh the finished weapon because even a 5-pound difference changes release timing. Throughout all of this, the bomb stays completely inert. The fuse has no power. The thermal battery that brings everything to life won't activate until the weapon experiences the sudden G-forces of release. Once each weapon passes inspection, it goes into climate-controlled trailers. But the weapons are the easy part. The hard part is proving that an airframe older than the crews flying it can still handle what's coming. Most military aircraft become obsolete within 30 years. The B-52's wings have logged over 21,000 flight hours, nearly double what they were designed for. And engineers say they won't hit their structural limits until the 2040s. Here's why. Instead of optimizing for one specific role, Boeing overbuilt everything. They added structural margin where it wasn't strictly necessary. They made components stronger than calculations demanded. They designed for maintenance by mechanics with wrenches, not specialists with computers. Maintainers work through the aircraft system by system, looking for anything that might fail over hostile territory. They check the wings first, running hands along the upper surface where stress concentrates every time the aircraft flexes during flight. These wings were designed for 12,000 flight hours. Most have logged over 21,000 and they're still going. Engineers calculate they won't hit their structural limits until the 2040s, nearly a century after they were built. 3 different bombers have been designed to replace this aircraft, but the B-52 outlasted all of them in no small part to its robust design. They inspect the fuel system with particular care. The B-52's fuel tanks are built directly into the wing structure. No separate containers, just sealed cavities in the wing itself. Engineers call this a wet wing design. It saves weight, but it means fuel is only separated from outside air by the wing skin and a system of seals and clamps. Those seals deteriorate over decades. Maintainers check every clamp and fitting for the weeping links that have plagued this fleet since the 1980s. Hydraulic lines get pressure tested. 4 separate systems, each running at 3,000 psi. Pressure high enough that a pinhole leak becomes a cutting jet. 4 systems means you can lose 1, lose 2, even lose 3 and still land the aircraft. That redundancy exists everywhere. Multiple electrical buses, backup instruments, redundant communications. Nothing fancy, just layers of systems that keep working when individual components fail. And then there's the landing gear. Maintainers check it with particular care because the B-52's gear doesn't work like anything else flying. Once the aircraft passes inspection, it's time to fill it with more ordnance than any other aircraft in the American inventory can carry. Weapons loaders positioned the JDAMs under the aircraft, each bomb sitting on a hydraulic lift that raises it into the weapons bay. Inside sits the rotary launcher, a revolver cylinder scaled up for bombs. This system was originally designed to carry nuclear gravity bombs during the Cold War. Now it holds GPS-guided JDAMs, but the mechanics haven't changed. 8 positions arranged in a circle, each holding a 2,000-pound weapon. The entire assembly spins 360 degrees in under 3 seconds, rotating the next bomb into release position while the aircraft lines up for its next target. Drop one bomb, the launcher spins, and the next weapon is ready before the first one hits the ground. But JDAMs are just one option. The same aircraft can carry cruise missiles that strike targets 500 miles away, naval mines that shut down empty ports, cluster munitions, laser-guided bombs. The newest addition, hypersonic missiles that travel faster than Mach 5. No other aircraft in the industry can carry this range of weapons. The B-52 doesn't specialize, it adapts. No matter the loadout, each weapon locks into suspension hooks rated for 14,000 pounds, 7 times the bomb's actual weight. That margin exists because G-forces multiply during combat maneuvers. A 2G turn doubles the load. Add turbulence and the numbers climb fast. Load crews connect the data cables that let each weapon talk to the aircraft. The mechanical connections have to be perfect. Off by the width of a penny, and the electrical interface won't seat properly, which means the bomb never learns where its target is. It falls dumb, guided by nothing but gravity and a prayer. But the most unusual feature of the B-52 isn't the weapons bay. It's underneath the aircraft. Something so strange that the Air Force classified photographs of it for years. But the B-52 doesn't stop at internal carriage. Unlike stealth bombers that hide everything inside radar-absorbing shells, the B-52 carries weapons anywhere they'll fit. External pylons under each wing hold 6 more weapons per side. A single, fully loaded B-52 carries 70,000 pounds of ordnance, more than any other aircraft in the American inventory. The weapons don't know where they're going yet. Target coordinates stay locked in the aircraft's computer until seconds before release. This allows targets to change mid-flight based on intelligence that didn't exist when the aircraft took off. The aircraft is loaded, 70,000 pounds of weapons ready to go. But the 5 people who have to deliver them face a problem. Because if something goes wrong, 2 of them may not be able to escape. At the flight equipment shop, specialists prepare gear that keeps crews alive at altitude and gives them options if everything fails. Oxygen masks get pressure tested for high altitude, where the air is too thin to sustain consciousness. Helmets contain flash protection that blocks the light of a nuclear detonation. Visors that can go from clear to opaque faster than nerves can register pain. Survival vests carry beacons, water purification, and signaling equipment for the possibility of ejecting over hostile territory thousands of miles from help. The B-52 has a 2-story crew compartment. Upper deck, pilot and co-pilot facing forward. Electronic warfare officer facing aft. Lower deck, radar navigator and navigator, surrounded by screens and weapon systems. This creates a problem. 4 crew members eject upward through the hatches above their heads, standard ejection seats that rocket them clear from the aircraft. But the 2 on the lower deck have nowhere to go but down. Their seats fire through hatches in the floor, blasting them beneath the aircraft. Minimum safe altitude, 250 feet, traveling at least 120 knots. Below that, the seats don't have enough distance to work before hitting the ground. If an ejection seat malfunctions, your only option is bailing out manually through the hole left by your crewmate's seat, if they got out. B-52 missions can stretch beyond 24 hours with aerial refueling. The longest combat sortie in history lasted 35 hours, from Louisiana to Iraq and back during Desert Storm. At those durations, the cramped compartment becomes an endurance test. 5 crew members ready, but getting this aircraft off the ground requires something no modern bomber needs. And during the Cold War, it was the difference between launching a nuclear strike and America becoming a parking lot. The B-52 can't start itself. Modern aircraft have auxiliary power units, small turbine engines that provide electricity and compressed air to spin up the main engines. The B-52 has nothing. It sits cold, dark, and quiet until ground equipment brings it to life. Normal startup means connecting a high-pressure air hose to the left wing. Compressed air spins the compressors on engines 3 and 4. Fuel flows, igniters fire. Once those engines stabilize, air from them starts the remaining 6 in sequence. The whole process takes over an hour. And for 2 decades, that hour was the difference between launching a nuclear strike and watching your entire base disappear in a Soviet fireball. Strategic Air Command kept B-52s loaded with nuclear weapons on constant alert, ready to launch at the first warning of Soviet missiles. Flight time for an ICBM from Siberia to the continental United States? About 30 minutes. By the time warning systems confirmed an attack was real and not a false alarm, crews might have 15 minutes to get airborne or watch their aircraft vaporize on the ramp along with everything else on base. So the Air Force developed a cartridge start. Explosive cartridges, 10 inches across, 8 pounds each, get loaded into ports on the engines. These are essentially oversized shotgun shells. When fired, they release a massive burst of pressurized gas that spins the compressors instantly. No external equipment needed. No waiting for ground support. Ground crews load the cartridges, pilots hit the switches, smoke erupts from the nacelles, and 8 engines roar to life simultaneously, from cold to taxiing in under 10 minutes. The engines themselves, Pratt & Whitney TF-33 turbofans, entered service in 1961. 17,000 pounds of thrust each, 136,000 pounds total. Pratt & Whitney stopped manufacturing them in 1984. The Air Force has kept them running through depot maintenance and parts salvaged from the boneyard. New engines are coming, but not until the 2030s. 8 engines are now running. The pilots work through their checks, including a system that will matter much more on the return trip than on departure. Before the aircraft moves, the navigation system needs to find itself. The inertial unit establishes its reference by sensing Earth's rotation, a process that takes 8 minutes of absolute stillness. If the aircraft moves during alignment, even bumped by the wind, the system starts over. GPS loads next, military encrypted, accurate to feet instead of meters. Taxiing requires thinking ahead in unnatural ways. The nose wheel sits 110 feet in front of the main gear, nearly the length of a basketball court. A turn that looks safe from the cockpit can put the main gear off the taxiway edge and into the grass. Pilots learn to drive the aircraft like they're steering a building on wheels, starting turns early and watching the wings constantly. At maximum weight, 488,000 pounds, the B-52s need most of the runway. There's no margin for error, no changing your mind past a certain speed. The pilots brief abort criteria before every takeoff. What speed they'll still try to stop, what speed they're committed to fly no matter what happens. Clearance comes, throttles advance, 8 engines spool to military power. 136 pounds of thrust pushes against 500,000 pounds of aircraft. The nose lifts. 185-foot wings flex upward, tips rising nearly 12 feet as they take the aircraft's weight, and the bomber breaks free. At cruise altitude, everything changes. The lumbering antique that needed a ground crew just to start its engines is now capable of destroying targets half a continent away without ever entering enemy airspace. The radar navigator watches 4 screens: radar returns, weapon status, navigation data, and threat warnings. The electronic warfare officer monitors for enemy radar trying to track them, ready to jam or deceive anything that locks on. The navigator maintains position and timing with backup calculations in case the electronics fail. The cockpit is a collision of eras. Original 1960s gauges and switches share panel space with modern digital displays showing moving maps and real-time intelligence feeds. A bomber built before the moon landing can receive targeting updates via satellite from commanders on the other side of the planet. Approaching the target, the crew runs the weapons checklist. They select which JDAM drops first. The rotary launcher spins, moving the weapon into release position. Bay doors stay closed until the last moment. Opening them early alerts anyone watching. Doors open. Through the umbilical, the aircraft floods the bomb with everything it needs. GPS coordinates to 10 decimal places. Wind speed at multiple altitudes, barometric pressure, and the angle to strike the target. Release. Hooks open. Ejectors shove the weapon clear of the aircraft. The instant the umbilical cord breaks, the bomb becomes autonomous. Thermal battery ignites, flooding the electronics with power. Fins deploy. GPS locks onto satellites. The JDAM doesn't fly. It falls with precision. Each fin adjusting, trading altitude for accuracy. In the final seconds, corrections come hundreds of times per second. The last adjustment happens a fraction of a second before impact. Then it hits. For heavily defended targets, the B-52 doesn't need to get close. Cruise missiles can strike from over 500 miles away. The bomber never enters enemy airspace. It launches from international waters or friendly territory, turns around, and goes home while the missiles do the dangerous work. This is what makes the B-52 impossible to replace. It's not a penetrating bomber anymore. It's an arsenal ship. A flying magazine that carries more firepower than a destroyer and can reposition anywhere on the planet in 24 hours. It can loiter for hours over a battlefield, waiting for targets to appear. It can launch hypersonic missiles that arrive faster than any defense can react. It can drop JDAMs on coordinates that didn't exist when it took off. The B-52 doesn't need stealth because it doesn't need to survive the target area. Just get weapons within range. But the mission isn't over, and returning home requires solving a physics problem so strange that Boeing's solution was classified for years: a landing gear that appears to be broken. The B-52 has a 185-foot wingspan and a vertical tail that catches crosswinds like a sail. Most large aircraft use tricycle gear. Main assembly spread wide under the wings, nose gear up front. Weight distributed on a stable triangle that naturally resists tipping. The B-52 uses bicycle gear. 4 main bogies arranged in a single line under the fuselage, one behind another. Small outrigger wheels near each wingtip keep the wings from scraping the ground, but they don't carry any real weight during landing. All that wing area and vertical tail surface catches crosswinds brutally, pushing the aircraft sideways as it slows down. With the main gear arranged in a narrow line rather than spread wide under the wings, there's almost nothing to resist that sideways push. Normal aircraft handle crosswinds by crabbing, pointing the nose into the wind during approach so the aircraft tracks straight toward the runway despite being pushed sideways. Just before touchdown, the pilot kicks the rudder to swing the nose around and align with the runway centerline. The B-52 can't do that. The wings are so long and hang so low that banking during that last-second decrab maneuver risks dragging a wingtip on concrete at 140 knots. So Boeing made the landing gear swivel. Both forward and aft main landing gear assemblies can rotate up to 20 degrees off the aircraft centerline. Before starting the approach, the pilot dials in the runway heading on a cockpit control. The gear rotates to align with that heading, completely independent of where the aircraft's nose is pointing. The result looks impossible. The B-52 approaches with its nose cocked to the wind, tracking toward the runway but pointing somewhere else entirely. In heavy crosswinds, pilots look out the side windows to see the runway instead of straight ahead. Then the aircraft touches down, still crabbed, nose still fighting the wind. The gear rolls straight down the center line while the fuselage points in another direction. The bomber appears to slide sideways, fuselage pointing one way, wheels rolling another. It looks broken. It looks like something has gone terribly wrong, but it's doing exactly what it was designed to do. This feature was classified for years after the B-52 entered service. Early photographs either hid the gear or used angles that didn't show the swivel. The gear touches, the aircraft rolls out crabbed, fuselage fighting the wind, gear tracking straight. Spoilers deploy, drag chutes blossom behind the tail, and a bomber older than most of the people watching it comes to a stop. And when the last one finally stops, somewhere after 2050, it will have served longer than any combat aircraft in history. Not because it was the fastest, not because it was invisible, but because Boeing built something in 1952 that could become whatever the future required. 100 years of warfare, carried on wings designed by engineers who never lived to see what they created. If you enjoyed this video, then you'll love our video on the B-2 bomber. Bye for now.